nothing beats, we're going to start looking at our derivative rules moving forward. And in this video, we're going to come up with some initial rules for differentiation, and we're also going to look at the first form of what is called the power rule. Let's get going here. All right, first little rule we got, derivative of a constant. So suppose you got a function that's just a constant function, some real number here. Then, of course, the graph of this function is going to be a horizontal line, and that horizontal line always has a slope of 0, and thus the derivative of a constant with respect to its input variable, in this case x, is always going to be 0. So nothing quite that amazing so far, but got to state that idea. And of course, here's the graph of a constant function. F of x is some constant c. And as we can see, the slope is always 0. So there's one rule. But let's get a little more into it here. Let's consider a power function of the form, say, f of x is x to the n. And over here, what we're saying is n is a natural number or 0. So just think of n is 0, 1, 2, 3, 4, and so on. Some positive whole number, but it could also be 0. So our goal is to figure out down here what the derivative of that power function is. So we're going to figure it out. Now, we can use the definition of the derivative function to come up with this statement right down here. So f prime of x, which of course is the same as the derivative of x to the n with respect to x here. By definition, limit as h goes to 0 of f of x plus h minus f of x divided by h. And in this case, our f is x to the n, and so we get this limit right here, limit as h goes to 0 of x plus h to the n minus x to the n divided by h. So as h goes to 0 there, of course, that goes to indeterminate form 0 divided by 0. And so we got to have some kind of method. What are we going to do to figure out what this limit actually is, since n is any arbitrary positive whole number or 0? If n was 1 trillion, that would take a long time to expand that binomial. Lucky for us, we've got a trick up our sleeve. And that is, let's recall real quick, Pascal's triangle. This is a way to figure out the coefficients of the terms in the binomial expansion. Let's say something plus something, a plus b, whatever those expressions are, quantity to the n power. So if you multiply that entire thing out, we get the coefficients given by Pascal's triangle, and that triangle looks like this. So right here, you can think of this as a plus b to the 0 power. This right here, a plus b to the 1 power. So you think, okay, a plus b to the 0 power, that's just 1. It's literally the number 1. A plus b to the first power, well, that's a plus b. So the 1 and the 1 in that row represent the coefficients of the a and the b. This right here, the coefficients of a plus b squared. So if you square that out, you get a squared plus 2ab plus b squared. So you can see the coefficients 1, 2, 1. Or right here, a plus b quantity cubed, which gives a cubed plus a 3a squared b plus a 3a b squared plus a b cubed. So you can see the pattern, 1, 3, 3, 1, the coefficients. So we could just keep going on forever with this, and Pascal, of course, is famous for coming up with this. And so that's going to help us rewrite our limit. Okay, so you think about that triangle in the back of our head here. Let's go back to our limit that we were trying to find, the derivative of the function x to the n. We were right here, right? So now that we have the Pascal's triangle as a refresher, we can apply this to the x plus h to the n power. So instead of having a plus b to the n power is just x plus h to the n power here. Now, when I do that, notice the pattern up here with the coefficients. When you look at the little exponents here, 0, 1, 2, 3, and so on, you notice that those exponents appear throughout each of the corresponding rows. And of course, the first coefficient is always a 1, the last coefficient is always a 1, and then there's stuff in between. Now, when we take that into consideration, and I rewrite x plus h to the n here, that's all of this stuff right here. So take note. The very first term is always that first term in the binomial, in this case x, raised to that n power. And then the next term is always going to be that coefficient n, which is the same as the power, and then we reduce the power of x here by 1, so nx to the n minus 1, and then we add in that h multiplied to it. And then as we go through all these terms here, right, the coefficients are sitting around, and then each power of x is decreasing while each power of h is increasing, all the way down to the second to last term right here, which is going to have another coefficient of n, and then the first power of x, h to the n minus 1, and finally the very last term is just coefficient 1, h to that n power. So I'm using the Pascal's triangle to expand that binomial, and then don't forget we have to subtract f of x still out here, all divided by h. So that really helps because now, as we can see, we have an x to the n minus an x to the n. So those two terms are just going to go away, and we'll be left with what we're left with. So after I subtract x to the n and x to the n from each other, I get this step. And notice that all the terms in the numerator have a factor of at least an h in them. And so what I do next is every single one of these terms, all of them, I reduce the power of h by 1 so that it cancels out with the common factor of h down in the denominator. So when we do that, we're left with this inside of our limit. Notice the very first term is going to be a nx to the n minus 1 since those h's canceled like so. And then all the rest of the terms have at least another power of h left over. And so they all get reduced by 1 power. That's why we see these last two terms written out right there. And so now, because I don't have indeterminate form, I can take this limit, and every single term that has a factor of h in it, which is all of this stuff right here, that all goes to 0. And thus, I'm left with n times x to the n minus 1. And that is the derivative of the power function x to the n when the power is a positive whole number or it's 0. And so, there's the power rule, the initial form of the power rule, given right here. Derivative of a power function that we've been talking about, x to the n when n is a whole positive number or 0, is n times x to the n minus 1. So to differentiate that power function, the power itself, the exponent, comes down as the coefficient, and you lower the exponent by 1. So there's a big rule. It takes care of a big family of functions. And now that we have that rule, let's just find a few real quick. Let's find each of the following derivatives that we see here on the screen. In part A, derivative with respect to x of x to the 8th. So notice that just of the form that we were just talking about, right? Power function, x to the 8th power. So what do? We bring down the power 8 in front times x, and then really to the 8 minus 1 power, which is 8x to the 7th. Once you do this 100 times, we don't even have to write that step in between, really. Similarly, in part B, the derivative with respect to p now of p to the 12th, well, again, it's a power function, right? So bring down the 12 times p, lower the 12 by 1, to get 12p to the 11th. So it's as simple as that. Nice to not have to use the limit definition every single time. In part C here, it's almost like a trick. Notice we are asked to find the derivative with respect to q of y to the 5th. Now remember our Leibniz notation. This q down there tells us to treat q as the input variable. I don't have any terms with q's in them in y to the 5th, so really what we're being asked to do here is differentiate a constant, because the input variable is q, and we're differentiating y to the 5th, and so y to the 5th is a constant in this case, and thus we get just 0. So there's a few quick examples of using the power rule. But there's other stuff here we got to talk about in this video. One being the constant multiplier rule. And so let's just suppose we got a real constant c, and we have a function f of x that is assumed to be differentiable, meaning we can find the derivative of it. Then the claim is that the derivative with respect to x of a constant times the differentiable function f is the same as the constant times the derivative of the function. So it's just saying, if you have a constant in front of your function and you're differentiating that whole thing, that constant multiple just sticks around for the ride throughout the entire differentiation process. And though we're not going to prove this rule right here, it's really just a direct result of limits, right? So if f of x is differentiable, limit as h goes to 0 of f of x plus h minus f of x divided by h exists. And if I have a common factor of a c appearing in the numerator, I can just pull that out using limit laws. That's really where it comes from. So now that we have that rule, find a couple more derivatives. You just kind of increase the complexity of the functions just a little bit here. So in part A, we're asked to find the derivative with respect to x of now -5 times x to the 7th. So it's really a power rule and a constant multiplier rule combined. And so we can think of this as -5 times the derivative with respect to x of x to the 7th. And we know x to the 7th is differentiable. It's that power functions that we were discussing a moment ago. So then that's just going to be a -5 times, bring down the 7, x to the lower the 7 by 1, so 6 power, giving us a -35 x to the 6. There's the derivative function of -5 x to the 7th. And in part B, very similar, we are differentiating with respect to p here, the function 8p to the 10th. So again, constant multiple, you could think of it as 8 times the derivative with respect to p of p to the 10th. And then we apply our power rule. We get an 8 times, bring down the 10, times p, lower 10 by 1, so 9th power, giving us 80p to the 9th. Much quicker than using limit definition every time. So it's nice once we develop these rules. Okay, what else? Another initial rule, sum and difference rules for differentiation. Let's suppose now we got two functions, say f of x and g of x, and they are both assumed to be differentiable. Then, if I take the derivative of the sum of the two functions, say f of x plus g of x, that's the same as the sum of their corresponding derivatives. So this allows us to differentiate term by term if we have a whole bunch of terms in one single function rule. And then similarly, the difference rule, if I take the derivative of the difference of the two functions f and g here, then we get it is the difference of their individual derivatives. So again, differentiating term by term, and it doesn't matter if there's a plus or minus in between the terms, still combining them. Now you try to think why that's true, right? And to go back to the limit definition of the derivative again, we have limit laws for sums and differences, right? So you just keep that in the back of your head that, well, yeah, it's just a direct result of that because we're assuming f and g are differentiable, so their limit definitions of their derivatives exist in the first place. So this for at least this video, allows us to now differentiate polynomial functions, since polynomial functions are just sums of power functions where the powers are positive whole numbers or zero. Then we can apply all three rules now, right? The power rule that we've established in this one. And by the way, the power rule does get more intricate as we get deeper in the sections, but for now we just stick to whole positive powers or zero. And you can see we've got power rules, we got constant multiplier rules here, and we got sums and differences rules for derivatives. So let's find this derivative of this fifth degree polynomial. And I'm just going to write it out, entirely this first time, but as we get better and better at taking our derivatives, this maybe is just a one-step kind of answer. But just to see the rules at place, I'm going to rewrite this as, okay, going through term by term here, okay? The first one, I got that constant multiple as well, right? Negative 12 times the derivative with respect to x of x to the fifth, plus the next one, a 9 times the derivative with respect to x of x to the fourth, minus a 7 times the derivative with respect to x of x cubed, plus a 16 times the derivative with respect to x of x squared, almost there, minus a 3 times the derivative with respect to x of x, and finally, plus the derivative with respect to x of pi. So what I did there in that step, right, is I applied the constant multiple rule for derivatives, pulling out the constant multiple from each of the terms in front of the derivative. And then because I'm taking the derivative of a sum and difference of terms here, I also wrote it out as the sum and differences of the individual derivatives. Differentiate term by term. So let's go ahead and just finish it. This is going to be a negative 12 power rule times a 5x to the fourth power plus a 9 times power rule again, 4x cubed, minus that 7 power rule times a 3, x squared, plus a 16 power rule times a 2 times just a single power of x, and then minus a 3, and then technically times 1, right? X is a linear function with slope 1, but technically you can use the power rule there, bring down the power of 1, lower that by 1, giving us 1 times x to the 0 power, which of course is just 1. And then the last term, derivative with respect to x of pi, well, pi is a constant function, right? So that derivative is just a 0 for that last term. So finally, we just clean it up, multiply this out, we get a negative 60 x to the fourth plus a 36 x cubed minus a 21x squared plus a 32x minus a 3. And there you have it. There is the derivative of that fifth degree polynomial, combining three different rules that we've established in this video. And that is the end of the video. So that's that first video on coming up with some initial differentiation rules. What we're going to look at next is we're going to start venturing into derivatives of exponential functions, and specifically e to the x is what we'll focus on first. So that's it. Hopefully that helps you. This is Math and Beats, and I'm out of here.